In this video, we're going to learn about the trig functions when applied to certain special angles. These are going to be some of the only angles that we can write down the perfect correct answer of the trig functions, and everything else we're going to have to make a lot of approximations for the angles, but that's okay. So for the first one is where we're going to have a 45, 45, 90 right triangle. And what you're supposed to remember from, say, geometry class is that in a 45, 45, 90, it's isosceles, which means your two legs are equal size. We can pick whatever number we want to. I'm going to choose 1 because it makes our life a little bit easier here. But if you picked 3 or 5 or 17, whatever you want, you're still going to get the same answers. Once we have our two legs, we can go ahead and find the hypotenuse by Pythagorean theorem. It's going to work out to be square root of 2. And once we have those sides, then we can just use our sine, cosine, tangent, our SOHCAHTOA here. So sine is opposite over hypotenuse. That's going to be 1 over root 2. Cosine is adjacent over hypotenuse, 1 over root 2. And tangent's opposite over adjacent, 1 over 1 is 1. I will say that some people prefer not to leave the squares in the denominator, and so you could do what's called rationalizing them, and if you did that, it would be working out as square root 2 over 2. Now mathematically it's the same number, it's a different way of writing it, and again, depending on who you talk to, some prefer it one way or the other. Personally, I'm not that I don't think it's that important which way you write it, so I'm fine with either way, but it's good to know both of them. One of the reasons why I like leaving it in the original form of 1 over root 2 is when I go to find my reciprocals here, my cosecants, the reciprocal of 1 over root 2 is going to be just root 2, whereas if you reciprocaled root 2 over 2, you would have had to simplify it back down to just root 2. Similarly, secant is going to be 1 over the cosine is root 2. Cotangents, the reciprocal of tangent, reciprocal of 1 is 1. And so there we go. Now for the 30, 60, 90 right triangle, it's going to be a little bit more work because the two smaller angles are different. One is 30, one is 60. So we have to go through for both sides here, 30 and 60. And I'll just go ahead and just call them that way. Obviously my triangle is not drawn to scale here, but that's okay. Now for 30, 60, 90 right triangle, what you're supposed to remember from geometry again is that if you pick the opposite side to be 1, then the hypotenuse becomes 2 and the other leg becomes root 3. That's just the 30, 60, 90 right triangle there. So for sine of 30, the opposite of 30 is 1. The hypotenuse is 2, so we get 1/2. Cosine of 30 is the adjacent over hypotenuse. And lastly, tangent would be opposite over adjacent, 1 over root 3 here. Then we can do our three reciprocals. Reciprocal of 1/2 is 2. This one's going to be 2 over root 3, which again, if you wanted to, you could go ahead and rationalize this. And cotangent would be then root 3. Now for sine of 60, so now we're looking at the 60 degree. This time the one that's opposite is going to be the root 3. So it would be root 3 over 2, 1 over 2, opposite over adjacent is root 3. And then our three reciprocals again. And so at this point, I do want to kind of point out this certain fact here, that when I have a triangle, and I'm not going to say it's just 30, 60, 90 anymore, I'm going to say it's any angle here, and I want to find the sine of this angle. Sine is opposite over hypotenuse. So those would be the two legs I would use for sine of theta here. Now I'm going to go ahead and call this, I don't know, alpha. It's a different angle. And if I wanted to find cosine of alpha would be adjacent over hypotenuse. And notice how we're using the same two sides to calculate that. So what that means is that sine of theta is the same as cosine of alpha. And so this is what the co part stands for. The co in cosine stands for complementary angle. And so you see, when you have a right triangle, the two acute angles there are going to be complementary. They add up to 90 degrees. And so whenever you're trying to find cosine of one, it's the same as sine of the other, and vice versa. And the same thing with cosecant versus secant, cotangent versus tangent. All of those cos just stand for the complementary angle here. Now, on this bottom part here, I added a nice little word problem. I think it's a fun little experiment you can actually go out and do yourself if you're interested. But the idea is you go outside of a building, you count how many feet away you walk from it. So in this case, I decided to say that we walked 10 feet from it. And then we determine that there's a 60-degree angle of elevation. So angle of elevation is just saying what is the angle when you're looking up. So it would be 60 degrees here. And if I were just to make it look a little nicer and just draw the triangle, I have a 60-degree angle here. I know this side is 10 feet. And what I'm interested in doing is I want to find out what is the height h, this side of the triangle. So what I can do is I can say, well, I know the 10 feet side. I'm trying to find the h side here. What trig function uses those two sides? It'd be tangent. So I would have tangent of 60 happens to be opposite over adjacent. And if I solve for this, that means h is 10 tangent 60. But here's the problem, is that we actually know what tangent 60 is. Based on this work we did up here, tangent 60 is root 3. So h would be equal to 10 root 3 feet. And there we just found out the height of the building by just measuring how far we walked away from it and figuring out the angle that if you look up to the roof, what it's going to be. So this gives you a way to find out how tall a building is without actually trying to measure the side of the building, which would be pretty much impossible task for most people to do that. Right? You're not going to make a ruler as tall as the building is, and otherwise it's, how else you're going to do it. I will say that my calculations here are a little bit off because I did not include the fact that I'm actually standing here and looking up. So it's really a different triangle to look at here. But this answer would be correct at least if you were getting the angle of elevation based off of the ground. And so just think about how you can modify that if you wanted to do a real world problem here.